Welcome to This Explainer. Today, we're diving into an incredible journey that traces the very foundation of human manufacturing. We're going to start all the way back with the primitive scraping of wood and stone and work our way up to the mind-bending acoustic physics of modern nanomachining. It's literally a story of how we learn to shape the world around us and what actually happens when the materials we want to shape suddenly become a whole lot harder than the tools we have to shape them.
Okay, let's take a quick look at our roadmap. We'll start with the quest for precision. Compare cutting versus scraping, hit the modern material wall, then enter the wild world of ultrasonic machining, break down the anatomy of the machine, and finally, master the vibration.
Section 1. The quest for precision. You know, the fundamental human need for perfect parts.
Think about the ultimate goal of manufacturing. It's always been about creating interchangeable parts that assemble perfectly and function reliably for years. And if we look back at our history, we've made a massive sprint. We went from early hand tools made of sticks and bones straight into power-driven industry. A huge game-changer hit in 1774, when John Wilkinson built a boring machine for steam engine cylinders, which solved some major mechanical headaches. Then, boom, jumped to 1953 with CNC, computer numerical control machines bringing unprecedented accuracy. And today, we're down to nanomachining. We are literally removing material atom by atom to meet the intense demands of aerospace. It's wild.
Moving right along to Section 2, Cutting versus Scraping, looking at traditional machining physics.
So, there's a really clear physical difference between the two main types of traditional machining. On one side, you've got machining by abrasion. Think grinding or honing. You've got these randomly oriented, hard abrasive grits taking these really shallow, uneven bites out of the material. The chips are so minute you literally can't even see them with the naked eye. But then, on the flip side, you have machining by cutting, like using a lathe or a drill. Here, your tool has a highly specific, exact geometry. It penetrates to a targeted depth and carves off visible, obvious chips of metal.
But here is the absolutely crucial point. Whether you're cutting or abrading, traditional machining completely relies on one unbreakable rule of physics. Your tool must physically be harder than the material you're trying to shape. It's just common sense, right? If it isn't, your tool breaks, not the workpiece.
Which leads us perfectly into Section 3. The modern material wall. Or what happens when materials fight back.
See, the modern era introduced ultra-hard ceramics, inorganic glasses, and advanced composites. And these materials? They completely destroy traditional cutters. If you tried to machine them the old-fashioned way, the volume of your worn-out tool is often higher than the volume of the metal you actually managed to remove. This created a severe crisis. Industries desperately needed micro-machined, complex shapes with flawless surfaces, but the cost of tool damage was just astronomical.
So this brings us to a huge narrative pivot in our explainer. What do you actually do when you're handed a piece of material that is harder than literally any tool in your shop? How on earth do you cut the uncuttable?
Well, let's look at Section 4, Enter Ultrasonic Machining, where we basically start breaking the old rules of physics. Enter ultrasonic machining, or USM. Patented back in 1945 by L. Balamuth, this is a brilliant mechanical process that totally bypasses the need for a harder cutting edge. Instead of using a sharp, rigid blade, USM uses high-frequency acoustics and liquid abrasion to machine materials with extremely low ductility, meaning materials that are super hard and brittle, like quartz or those advanced ceramics we just talked about.
Looking closely at how this actually works, you have a transducer at the top sending ultrasonic vibrations right down through an acoustic horn. That horn drives the USM tool, which, and this is the crazy part, is actually hovering just 25 to 60 micrometers above the workpiece. It never actually touches. At the exact same time, a pump floods that microscopic gap with an abrasive slurry. So the tool isn't cutting at all. It's rapidly hammering those tiny abrasive particles into the surface to make these unbelievably precise cuts.
All right, on to Section 5, Anatomy of the Machine. We are essentially building a microscopic jackhammer here.
The whole operation relies on the perfect harmony of four key subsystems. It starts with the power supply, moves to the transducer which generates the motion, down to the acoustic horn which amplifies it, and finally, it relies heavily on that constant flow from the abrasive fluid system.
So it all kicks off with the power supply. And no, you're not just plugging this into a standard wall outlet. The power supply converts standard 50 Hz electrical power into an incredible 20 kHz frequency sine wave.
That means it is oscillating the machine's components over 20,000 times a second. That is way, way beyond the range of human hearing. Now, the acoustic horn is absolutely vital because it acts as a mechanical amplifier. See, the transducer core, which is often a magnetostrictor, changing shape under a magnetic field, only elongates by a tiny microscopic fraction. We're talking sometimes just 0.001 micrometers. You can't do any real work with that. So, the acoustic horn takes that microscopic flex and physically magnifies it through its carefully designed shape, turning it into a very practical 40 to 50 micrometer stroke right at the tooltip.
Which brings us to Section 6, mastering the vibration and the actual physics of material removal.
So, actually removing the material doesn't just happen in one simple way. It's a combination of 3 distinct, perfectly synchronized phases. First, you've got direct mechanical abrasion, where the tool is hammering the abrasive grains straight into the surface. Second is microchipping. This is where particles in the slurry get violently knocked across that microscopic gap, hitting the workpiece like tiny projectiles. And third, fluid erosion.
And that final erosion phase is honestly mind-blowing. The high-frequency vibration creates these cavitation bubbles right inside the liquid slurry. When those microscopic bubbles collapse against the work surface, they generate localized pressures of over 1,000 kilograms force per square centimeter. It's basically a localized microscopic explosion that literally erodes the hard material right off.
Now, to master this whole process and optimize what engineers call the material removal rate, or MRR, an operator has to perfectly balance 4 categories of variables. You have to consider the brittleness of your workpiece, the mass and shape of your tool, the operating frequency, and some very specific slurry details, like are you using boron carbide or silicon carbide? Is the grit size 100 or closer to 800? Plus, if your downward static load is too heavy, the slurry gets completely starved out. But if it's too light, you just don't get enough impact force. So, if there's one crucial takeaway for achieving maximum efficiency here, like the real secret sauce of ultrasonic machining, it's this exact balancing act. Your physical abrasive grain size must perfectly match your acoustic vibration amplitude. When that physical grit aligns perfectly with the size of the microscopic hammer stroke, you hit absolute machining harmony. As we wrap up this explainer, just think about the journey we've taken today. We literally went from hitting rocks with sticks to vaporizing advanced ceramics using 20 kilohertz sound waves. It leaves us with a really fascinating thought. If we are already removing material atom by atom using nothing but sound and suspended liquid particles, completely bypassing the physical limits of hardness, what impossible materials and what unimaginable engineering challenges will human ingenuity conquer next? Thanks for exploring this with us, and keep questioning the physical world around you.